Hello ladies and gentlemen, welcome back to GGS 300 to Quantitative Methods for Spatial Science. Today we're going to be focusing on Lab 9, which is on Inferential Spatial Statistics, and hopefully you've been able to look on Blackboard and basically download the GIS data that's uploaded there, but also the walkthrough instructions that I'm going to show you now, and we're going to tap away ArcMap and produce some of those inferential spatial statistics tests, the results for those tests that we covered theoretically within the lecture. But now we're going to actually do that using some spatial point data and some spatial polygons for different parts of the US and the US as a whole. So without much further ado, let's progress. So what I've done is I've just opened up ArcGIS here, and I've just got a blank project, and essentially I've downloaded the data, and what I'm going to do is I'm going to import those shapefiles straight into ArcMap, and I'm just going to drag and drop those points. There we go. Great. So let me just add a background to this. For some reason, it's not allowing me to insert the map I wanted, unfortunately. Okay, my apologies. As a quantum GIS user, whenever I use ArcMap, I have to remind myself of how to find certain things. But great, so now we've got, within this context, is some data for nesting sites just to the northeast of Austin in Texas. And what we've essentially got are points for the recorded nesting sites, and then we've got a neighborhood polygon, so it just draws the boundary around the outside. Okay, so I hope you're able to download that and follow along with me. So first we're going to focus on nearest neighbor. So as I've already explained, these are points for bird nests. The question therefore is, well, are the nests actually randomly placed within the neighborhood or not? Is there some other sort of process going on? Okay, so for the null hypothesis, we would assume that the mean nearest neighbor distance would be equal to the random mean nearest neighbor distance. Whereas the alternative hypothesis would be essentially that these two mean values would be significantly different. Okay, so how do we do that? Well, in ArcMap, what we need to do first is go to the Arc toolbox. Okay, so let's do that. Analysis, we need to go to the tools. Okay, then we need to go down to the Spatial Statistics toolbox. Okay, so Spatial Statistic Tools, Analyzing Patterns, and then Average Nearest Neighbor. Okay, so analyzing patterns here you can see, and then we can find the average nearest neighbor. Then what we're able to do is to input the nests layer, and we're able to define the distance measured being Euclidean, and we're able to generate a report for that. So let's just, first time round, let's add an area value for that. So let's just say it's 600,000 square meters. Let's generate a report, and then let's run that. Okay, let's view the details, and let's go down to the message and see the full output. So what we have is we've run an average nearest neighbor analysis, we've got the summary for it, and this produces our observed mean distance, which is about 9.4, the expected mean distance, which is about 21.9, and the nearest neighbor ratio, which is about 0.43. And this produces a z-score of -19 and a highly significant p-value that allows us to be more than 1% significantly confident that 1% confident that these results haven't just occurred by chance, essentially. So there's a highly significant effect going on here. When you compare those stats to what we've got in the walkthrough, you'll see that we've got pretty much exactly the same. So the question is, well, what are we actually going to do with these results? Well, obviously we're going to reject the null hypothesis, and we're going to conclude that the placement therefore isn't just random. There's some sort of significant spatial process which is leading to this type of outcome. So we can rerun the report now. So essentially we can rerun it without the area. So at the moment we've just exogenously defined what that area is. We can rerun it without this and have a look at the results. Okay, go into the mean results. And we do get reasonably similar results. What we get is a slightly different expected value, which is actually larger in this instance, but we still have a very large z-score and a very highly significant p-value. Okay, so it doesn't really change our conclusion very much depending on the area that we've defined. You can save this now, otherwise you could just open a new map, new project, and we'll be able to import the county data that you should also have, which actually contains a lot of statistical information. So I'm just going to cheat. I'm just going to remove these layers, and what I'm going to do is just drop in the shapefile into our workspace. Okay, so there we go. There is the shapefile of interest. So we've got all of these counties for the US. Obviously we want to have a look at the data that we've got. So if we go into the attribute table, you'll see that we actually have a lot of information. So name, state name, IDs, area, population from various different census age, census dates. We have demographic information, so racial, gender, age, and then some other general metrics that might be interested for socioeconomic analysis or economic analysis. Okay. So let's go back now and have a look at what we intend to do in this particular case. So we're going to focus in this example on Moran's eye. First we want to just understand a little bit about the map. Okay, so we're going to go and look at symbology for the layer. So here we go. There we go. So we've got the symbology, and what we'd quite like to do is look at the graduated colors. Okay. So at the moment this is actually showing the graduated color for area, as you can see quite clearly, and actually these are quintiles, so they've just broken the distribution down into 5 different classes. Yeah, yes, natural breaks. So this would actually be our quantile approach. Okay, so that just gives you a flavor for the data. Now what we want to do here is first we want to look at Hispanic. Okay, so we're going to go in and look at one of the racial demographic indicators. So up at the field level, run down and look at the Hispanic level. And then also we can normalize against the population rate for the year 2000. And okay, great. So now what that's doing is we've basically said, give us the number of Hispanic people. I think actually this is a percentage value. Let me just check that in the attribute table. Always good to know your units. No, so these are raw numbers. And we've got the natural breaks, so Jenks just here. And what we're doing is we're breaking down the distribution to understand where we've had the largest rate change against the normalization year, which is the population in the year 2000. So this is giving a very clear indication as to where there have been changes since the year 2000 in this particular demographic racial group. Okay. So now let's have a look for males against the year 2000. So again, this is going to be showing the proportion of individuals who are male against that census year value. So there's less of a spatial pattern now for these particular changes, but we do have the proportions over here on the right hand side. Okay. Now what we want to do is let's play with some statistical processes, some statistical tests. So let's go and carry out a spatial autocorrelation Moran's eye test for the Hispanic rate, for example. So let's go to the statistical toolbox. So I'm in it here. I just went to geoprocessing over here. And we want to go down to analyzing patterns and then to spatial autocorrelation. And what we want to do is input the feature layer first, which is low 48 county. And then what we want to do is to input the racial demographic metric Hispanic, as we have here. And this time around, actually, we'd quite like to get the HISP rate. So it's actually already been generated within the data set that you've got. So here's the Hispanic rate. What we want to do is to just set the spatial relationships to contiguity edges only, okay? And then we want to set that we generate a report, and then we want to look at the results. So let's run. This time it's taking quite a bit longer, so there's more data, and I would say that ArcGIS is generally slower than Quantum GIS in my experience. This is taking quite a bit of time, but it does have to do quite a few different calculations in order to get to this point. So I'm trying to think how many counties we have within our data set here. Let me just take a look. So we've got about 3,108 individual polygons which need to be analysed within the spatial test. There were a couple of features which clearly didn't run up here, but they're only a very minor number. And then we're able to obtain some metrics out of this. So look at the results. And then basically interpret them. So we've got a Moran's index of 0.82. So remember, Moran's eye essentially runs between -1 and +1. So let me just pull up where we are with those numbers, and we can interpret that correctly. Great. So from Moran's eye, remember from the lecture, if it's below 0, then it's dispersed. And if it's over 0, then it's more clustered. Okay, and we're actually getting quite a strong clustering effect here for the Hispanic rate change that we wanted to capture. Okay, and quite significantly higher than the expected index. Okay. And when we look at the z-score, we're getting 74.8, so it's incredibly large, which is providing a highly significant p-value. At more than the 1% confidence rate, we can be confident that the results haven't just occurred by chance, that we can reject the null hypothesis, and that we can actually accept the alternative hypothesis in this particular instance. So there is something beyond randomness taking place here, which has led to this type of clustering, essentially. Okay, now you can do the same actually using the inverse distance. Okay, so we can go back to the spatial statistical processing toolbox and go into spatial autocorrelation, a global Moran's eye, and then we're able to actually change the conceptualization of the spatial relationship and change it to inverse distance. We can use the Euclidean distance, that's fine, and we can just run this and see what results we're able to generate. So that definitely ran a lot quicker this time round. So let me just expand this so everyone can see. Okay, so here are our results. And again, what we're finding is still highly clustered, so 0.78 for the Moran's index. And the z-score, actually it's up at 135.055, so it's very, very large. And that's providing us with a p-value, which is very, very small. It's a highly significant finding for this particular instance, so the Hispanic rate and the level of clustering that's taking place. Okay, so hopefully you're able to run that and actually have a play around with how we've changed the values there based on different types of statistical tests. And now we can also change to the male rate. So let's try use inverse distance weighting with a distance band of 200. So let me just go back and change the input field. So we've got the male rates just here. So this is male. And what we'd like to do first time around is use the inverse distance, fine. Use a distance band of 200,000. So we're in meters in this particular projection. 200,000, okay. So that's 2 to the 5. And let's run that, 2 to 10 to the 5. Okay, and that's completed. So now let's have a look at the results that we were able to obtain. So the Moran's index is about 0.11, so it's ever so slightly clustered, but not really. I mean, it's not a hugely strong effect, but it does produce a large z-score, so it's 27.1, and again a highly significant p-value. So actually, this is a highly significant finding, even if the clustering isn't as strong as the previous example that we looked at. So a strong amount of spatial autocorrelation taking place here. We can also do some outlier analysis, so we can go into the spatial statistical toolbox and look at mapping clusters. So let's have a go at doing that now. So we're in the spatial statistical toolbox. Let's go down here to the mapping clusters area and let's look for cluster and outlier analysis. Okay, so here we go, I'm clicking in there now. We can focus on the Hispanic rate again using the inverse distance. So let me just select the input feature class first and then the field. So we want to go down to the Hispanic rate. We've got the inverse distance and we wanted to put a distance band on it of 200,000. Okay, so that's 2 times 10 to the 5, great. And now let's run. So it's taking a bit longer for us. And it's going to map out those cluster areas. Okay, fantastic, this is good. So we can see that the HH cluster, the high cluster, is in the southwest, so essentially along the border area, and also in South Florida, so just down here. But then we've got low clusters through the southeast, the midwest, and the northeast. So southeast here, the northeast, and the midwest area over here. So that's quite an interesting plot when we pull out and actually map the different outliers. That's interesting. So now let's focus on the male rate. So we can go back into the cluster and outlier analysis and we can change the rate that we want to actually map. So I've just changed the input field here to male. We're going to keep all of the other metrics basically the same, and I'm just going to run them now and we're going to see what we generate. So it's processing, starting to map out now. So that's interesting again. So we've got the high clusters over in this region in the west here. The high-low outliers are actually scattered along the Atlantic corridor. And then we've got some low-high outliers which are scattered across the south, the west, and indeed across Florida. And then most of our low clusters are in the deep south area, so running from Louisiana, Alabama, through Georgia, the Carolinas, all the way through Virginia, up into Pennsylvania and New York State, up to Maine, all the way along the coastline areas. So I think that there's some pretty nice plots that we're able to produce there using those cluster and outlier analysis tools. I hope that you're able to run along with the instructions which I've provided just here for you. Please have a go at doing this, and therefore you are able to kind of click around and play with the data that you've got, understand how to generate the data. I'm not sure of your existing level of GIS capabilities, but I think you've probably already done quite a few modules, so you should know how to use ArcMap. But it's important for you to kind of get into the spatial statistical toolbox if this is the main way that you intend to do some of the spatial analysis. And it's always good to be able to produce a nice looking map using ArcMap, for example, or some sort of GIS tool like this. So you've got the assignment now, and you've also looked at how we generate some of those metrics in this particular lab. You've got the theoretical understanding of how to generate these statistics. So I hope you're able to progress with the work. Let me know if you've got any issues, and I hope you enjoyed today's lab, and I'll see you all soon. Thank you. Goodbye.